Hello everyone, I am Hao Zhou from the Hong Kong Polytechnic University. I am very glad to present our paper entitled Happer, Unpacking Android Apps via a Hardware-Assisted Approach. App packing is a technique that is widely adopted by both benign apps and malicious apps. App packers deploy packing techniques to pack apps in order to prevent their bytecode from being analyzed. The technique is originally designed to protect intelligence properties of benign apps, such as protect them from being repackaged. However, it has been noticed by security researchers that packers are increasingly abused by malware. Meanwhile, it has been reported that packed malware can easily invade detection and sneak into app market, even the Google Play. Specifically, packers usually first hide the original bytecode of apps and then release the hidden bytecode to memory at runtime. For example, to hide the bytecode, some packers replace the original bytecode with fake ones, as shown in figure, the original bytecode is replaced with not instructions. The opposite of packing is unpacking, and its purpose is to recover the original bytecode of the packed app. Since the original bytecode will be released to memory at runtime, unpacks collect the released bytecode to achieve the purpose of unpacking. It is worth noting that, in order to prevent packed apps from being unpacked or be analyzed by unpackers, app packers also adopt anti-analysis methods. With the anti-analysis methods, unpackers cannot collect the released bytecode and then fail to unpack the packed apps. To defend against packed malware, various app unpackers have been proposed. Depending on how these unpacks are implemented, we divide them into 4 categories. First, the debugger-based unpackers such as KissKiss, which is a ptrace-based unpacker. However, packers can easily impact them by detecting the presence of debuggers such as ptrace. Second, the emulator-based unpacker such as Droid Unpack, and it is a QEMU-based unpacker. However, packers can easily impact them by detecting the presence of emulators such as QEMU. Third, the dynamic binary instrumentation framework-based unpackers such as Droid and PackerGrind, which are built upon the instrumentation frameworks Exposed and Evergreen, respectively. Packers can easily hinder them by finding their loaded binary files in memory. Fourth, the custom system-based unpackers such as AppSphere and Tira, which statically instrument the dev interpreter of the runtime Android to build a custom and system. Packers can hinder them by hooking the system library functions called by them for implementing unpacking. Since the existing tools can be easily detected by packers, they fail to effectively unpack packed apps. Accordingly, in this work, we proposed a hardware-assisted unpacker named Happer, which is much harder for packers to detect it. Happer can retrieve the hidden DEX data and assemble them into a valid DEX file effectively. Specifically, it tracks the packed app's runtime behaviors and dumps the hidden DEX data by leveraging the hardware features of ARM platform so that it cannot be easily impacted by packers. In addition, Happer can adaptively select proper unpacking strategies for unpacking rather than using fixed unpacking patterns. Precisely, Happer selects the proper DEX data collection points to collect the related hidden bytecode according to the observed packing behaviors. Moreover, Happer can extensively cover new packing behaviors. Specifically, we design a domain-specific language for analysis so that they can easily specify new packing behaviors to be tracked by Happer. In the following, I will first introduce the hardware features used by Happer, then I will elaborate the architecture overview of our tool and the technical problems we met and approached in implementing Happer. Subsequently, I will present the packing behaviors we identified in commercial app packers, followed by the evaluation results of Happer. At last, I will make a summary about our work. Happer leverages 3 hardware features of ARM version 8 platform to track executed instructions of packers and the demanded memory data such as the dynamically released bytecode to identify packing behaviors and unpack packed apps. Specifically, Happer uses embedded trace microcell, short for ETM, to trace the executed instructions of packers with no additional overhead. Meanwhile, it uses hardware breakpoints, short for HBRK, and the memory management unit, short for MMU, to interrupt the normal execution of packed apps, and then retrieve the demanded memory data in order to identify the packing behaviors and collect the release bytecode for unpacking packed apps. This figure shows the high-level overview of Happer, which consists of two parts: an ARM platform placed at the left side of the figure and a host computer placed on the right side of the figure. The ARM platform is responsible for conducting dynamic tracking, including tracing executed instructions, fetching the accessed memory data, and dumping the released bytecode. When monitoring runtime behaviors, Happer loads and parses the behavior specification written by the domain-specific language and then instructs the ARM platform to conduct the tracing task. Meanwhile, it retrieves the necessary runtime data for determining packing behaviors, including the executed instructions recorded by ETM and the demanded memory content fetched by hardware breakpoints and the memory management unit. The host computer takes the charge of controlling the tracing task, analyzing the retrieved information for uncovering packing behaviors, and assembling the collected data for unpacking. When analyzing packing behaviors, the host computer takes in the runtime information retrieved by the ARM platform. It parses the ETM string to recover the runtime method invocations conducted by the packers. Then it determines the packing behaviors according to the result of the method invocations and retrieves the memory content and dump the text data. When unpacking packed apps, according to the recognized packing behaviors, the host computer selects the proper text data collection points and instructs the ARM platform to dump the relevant text data. It is worth noting that, in some cases, packers just release hidden bytecode of app methods when they are loaded to Android runtime. To make packers release all these hidden bytecode at certain text data collection points, we insert additional instructions and force Android runtime to execute these instructions to load every app methods for collecting all the hidden bytecode for effectively unpacking packed apps. After retrieving all the hidden bytecode, the host computer assembles the retrieved text data to a valid text file for unpacking. To implement Happer, we tackle several technical challenges. First, we meet problems in tracking the executing instructions of packers. The on-chip buffer is too small to store in the ETM string. Meanwhile, since the executing instructions of all running processes will be recorded by default, the ETM string contains many redundant trace elements that are irrelevant to determining the packing behaviors, but handling such redundant data incurs obvious additional overhead. To tackle these problems, we use a dedicated off-chip hardware with a 4 GB buffer to store the ETM string and configure ETM to make it just track the executed instructions of the target app. Second, we encounter problems in resolving ETM string. Existing ETM string resolvers only focus on parsing the visual addresses of the tracked instructions. However, detecting packing behaviors also requires high-level semantic information such as framework and the native method implications. Hence, there is a semantic gap between the packing behaviors and the tracked instructions. To bridge this semantic gap, we design a new resolver to resolve instruction-level information from ETM string and then map them to native system library functions and framework methods by parsing the information from the loaded system library functions and the Android framework's OAT files. We come across problems in fetching memory data for identifying packing behaviors and unpacking packed apps. Happer works as an external debugger, and thus it needs to retrieve the data from physical memory. However, not all the data mapped in visual memory is loaded into physical memory by the operating system synchronously. To solve this problem, we insert extra instructions and force the operating system to execute the instructions to completely load the demanded data such that dynamically release text file in physical memory before Happer retrieves them. Currently, Happer supports the identification of 27 packing behaviors in 10 categories. This table lists the 10 categories of packing behaviors and their descriptions. The top 5 categories in the table are anti-analysis methods, which are employed by packers to prevent the packed apps from being analyzed and unpacked by unpackers. For example, packers adopt anti-debugging methods to check the presence of debuggers such as ptrace to detect debugger-based unpackers. Moreover, packers can examine the time delays incurred by dynamic analysis tools to detect instrumentation framework-based unpackers. In addition, some packers will hook debugging or unpacking related system library functions, such as the functions related to Android Locket, to make them invalid, and thus it can prevent custom system-based unpackers, which commonly call these system library functions, to complete these unpacking tasks. The remaining 5 categories in the table are bytecode hiding behaviors, and the packers use them to hide the original bytecode of the packed apps and prevent them from being easily retrieved by unpackers. For example, packers commonly dynamically load the hidden text file to memory. Moreover, we designed a domain-specific language for analysis to extend Happer for supporting the identification of new packing behaviors. Here shows an example of a behavior specification written by using the domain-specific language for identifying an anti-emulator behavior. Specifically, the language provides several functions to instruct the ARM platform to retrieve runtime information for determining packing behaviors. For example, getArgValue guides the ARM platform to get a parameter value of a system library function. We have applied Happer to analyzing packing behaviors and unpacking packed apps packed by 12 commercial packers, including the free online packing services provided by Ali, Baidu, Banco, Qihoo, Tencent, iJiami, Kiwi, and Testing. We have applied Happer to studying packing behaviors more than 24,000 benign apps. Among these apps, 1,712 of them have at least one packing behaviors, and all of these packed benign apps have bytecode hiding behaviors. Accordingly, we have applied Happer to studying the packing behaviors of more than 1,700 malicious apps and detected 214 packed malware. We apply Happer to identify packing behavior of commercial packers in order to answer the research questions whether Happer can identify more packing behaviors of commercial packers than previous studies. The table shows the detailed packing behaviors of commercial packers identified by Happer. In total, Happer identified all the 27 packing behaviors in 10 categories from the 12 commercial packers, whereas other 6 state-of-the-art unpackers recognize only 7 packing behaviors and 6 categories at most. Therefore, Happer identifies more packing behaviors than the previous studies. It is noteworthy that among the identified 27 packing behaviors, the details about 17 of them are disclosed for the first time. We apply Happer to unpack the apps packed by the 12 commercial packers in order to answer the research question whether Happer can unpack those packed apps. Happer can completely recover the text files of apps packed by 7 commercial packers. It is worth noting that Happer can collect all hidden bytecode of app methods, which is only released when the methods are loaded, whereas the other unpacks cannot. Meanwhile, Happer can partially recover the text files of apps packed by the remaining 5 commercial packers, including Baidu, Qihoo, and Testing. Since these packers re-implement the hidden bytecode using native code, the hidden bytecode will never be released to memory, and thus currently no unpackers can completely recover them. Since Happer can completely recover the original text file of apps packed by 7 commercial packers, while the other unpackers can completely unpack the apps packed by 5 commercial packers at most, Happer outperformed the existing unpackers in unpacking apps packed by the 12 commercial unpackers. We apply Happer to unpack the identified 214 packed malicious apps for the sake of answering the research question whether Happer can facilitate malware analysis. As shown in the table, before unpacking, almost no sensitive APIs are found in 207 out of 214 packed malware, which implies that packed malware can invade the anti-malware detection. However, from the recovered bytecode, many sensitive APIs are detected, which indicates that Happer recovers the malicious code of malware. Therefore, Happer can assist malware analysis to expose more stealthy behaviors of packed malware by providing their recovered text files. At last, I summarize our work. In this work, we propose the first hardware-assisted approach to scrutinizing the packing behaviors and then unpacking the packed apps accordingly. We developed a new unpacker named Happer after approaching several technical problems. We conduct extensive experiments on Happer, and the results show that Happer can effectively identify packing behaviors packers and recover the original bytecode of packed apps. In future work, we will extend Happer to support more packing behavior and discover new packing behaviors. Thanks for listening.